Next to the last chapter, chapters 8 and chapter 9 are on chemical bonding, and they're separated because there's so much material to cover. And we're going to take them in roughly, the concepts are roughly in chronological order as they developed, from very simple, just seat of the pants types of concepts, and then refine them into chapter 9. We'll get to the modern ideas of what a chemical bond is. Which brings us to this question: what do we mean by a chemical bond? Why do atoms bond with each other to form compounds? Why don't they just stay separate elements? I mean, wouldn't that be simpler? Just have 118 elements instead of billions of compounds? Well, I think that question answers itself. What we want to do is talk about chemical bond. What is a chemical bond, and how do atoms bond with each other? Because the evidence is there. They do bond, and there must be an advantage. We usually speak in terms of energy advantage. What's the energy advantage of atoms bonding together? Well, one of the first attempts at explaining the chemical bond was Dalton's atomic theory. Remember, John Dalton was, he proposed the atomic theory. We covered that already, I think, haven't we? Yeah. When he proposed the nature of the chemical reaction is based upon numbers and types of atoms combining with one another, and then in the chemical reaction, they just swap partners. So that means that bonds must be broken and then new bonds formed. Okay. That's an understatement. There's no simple and complete definition of a chemical bond at the same time. So we usually think of chemical bonds as whatever force holds groups of atoms together. Then we have some way of approaching the chemical bond from a quantitative standpoint, because force can be expressed in numbers and units of measure. Here's one thing that seems to be universal for all chemical bonds. In other words, a bond will form if the total energy of the aggregate, which we may call compounds, the total energy after the reaction is lower than it is before the reaction. Everything tends to run downhill. And lower energy is more stable. So if the amount of energy in the composite is lower than it was in the individual parts before the reaction, then we're assured to have a reaction. Now, where did all that extra energy go? Well, since we can't create energy and we can't destroy energy, it had to leave, right? It had to leave the system. And that implies an exothermic reaction. However, we do know of endothermic reactions that go spontaneously. There's this concept that if we look at it in these terms, where the reaction proceeds from left to right, this is just progress. And if we start here with reactants, and then we go through a series like that down here to products, and this is the energy scale. Have I used this diagram before? I don't think so. We'll get it in the second semester. But I'll give you a smattering now. This just says that the energy of the reactants before the reaction is higher than after the reaction, which means that this difference, that energy between here and here, had to leave. That change of energy leaves the system, and we know from our convention that it would have to be negative. Right? So, but sometimes we get reactions that are not exothermic, but endothermic. In other words, they go the other direction. Usually you have to force them to go back the other way. But sometimes, well, I can't make a blanket statement. What I'm thinking is if we draw that same diagram for something like nitroglycerin, right, it would be we start here and we go over here, and then we go into like a dip there, and then we go down like this. So the components of, we make nitroglycerin up here, right? So there's kind of a dip in here where it's relatively stable as long as you don't look at it cross-eyed. Right? But if you give it an excuse, it will jump this other hump and release all that energy. So I think we can still think of the chemical reaction, the formation of bonds, as favored if the products are lower in energy than the reactants. That's the takeaway from this whole discussion that I've been pounding for the last 10 minutes. And that's also a good statement. The system is always trying to achieve the lowest possible energy. In thermodynamics, we're just saying that the universe is running down. It started out, they think, at this level, and now it's down here like this. Useful energy is up here because you can take the process from here to here, and if you have your system arranged correctly, you can extract that energy and use it. But once it gets down to here, it's less useful. Okay, let's talk about the different types of bonds. The easiest one to understand is the ionic bond. And it's simply an electrostatic attraction between a positive and a negative ion. So in this case, sodium is the positive ion because it's a metal. Metals like to lose electrons, so that gives them a positive charge. And nonmetals like to acquire electrons. So if the difference in attraction is large enough, then the sodium will give up its electron to chlorine. Right? We would write it this way. That's a gas. And we would end up with this compound. Right? And so to balance it, we need two of these and two of those. So what happens is we get an electron transfer from sodium to chlorine. In fact, we need two of them. And that would give us the positive and negative charges that attract one another. And these ions that attract one another obey Coulomb's law. And if you've never had physics, I'll just show you what it is. There it is. This is Coulomb's law. Actually, that's our version of Coulomb's law. Coulomb's law is in terms of forces, either attractive or repulsive forces. So we have to, there's another term in there that we've removed because what we're interested in is the energy of attraction. And focus on the Q's, the Q1 and the Q2 of the charges. So if Q1 is positive and Q2 is negative, then this energy is going to be related to attraction. And R is the distance between their centers. Right? So if we had the sodium here and the chlorine here, then there'd be a center here and a center here, think nucleus. And the distance here is that little r. So the distance between them, as they get closer, right, the r decreases, right? R gets smaller. And since it's in the denominator, then the energy of attraction goes up. You get a stronger attraction as these get closer. So if this were some other ion that was, let's say fluorine, that was a smaller but still negative, then you would be able to get them closer together because fluorine is a smaller ion. And then the attractive energy would be much greater. Then also, if you have other ions in here that have different Q values, say you have a 2+ here, like let's say on the sodium side, magnesium. Let's do magnesium. Magnesium with a 2+, and say sulfur with a 2-, right? Then the increase in the size of the charge is related to Q1 and Q2. And that would also increase that energy of attraction because those terms are in the numerator. That's the whole point of this slide. All right, so we can calculate this energy of attraction between these two ions. If we know the distance between the nuclei and we know the charges, then we find that the attraction yields 8.37 times 10 to the minus 19 joules for each one of those pairs. And notice that energy is negative, which means as they come together, it gives it up. All right. Okay, we can look at it another way. Say we have, in case we have two identical atoms, now we're not going to have any ions, right? The only way we can bond these two is with a covalent bond. In other words, they have to share electrons. So we have to modify our thinking just a little bit for the covalent possibility. We're going to use the simplest possible covalent bond here between two hydrogen atoms. Remember, it's one of those diatomics. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomics at room temperature and 1 atmosphere pressure. And since hydrogen is the smallest representative of that group, then those nuclei can get really close and share that each one has an electron, can share 2 electrons. And the representation here is that as it gets closer, the electron density increases between the atoms. And you see less electron probabilities of finding electrons outside on either side of the nuclei. So electrons then tend to congregate in the middle to form that bond. What we're balancing here is the attractive force between the electrons of one atom and the protons of the other atom against the repulsive forces of the electrons of either atom and the protons of either atom, which will push them away. So we have to find a balance. How close can it get and find the optimum force of attraction between the two before those repulsive forces keep them further apart. So I think that's what coming up in the next slide. So when we look at this slide, it's best to understand this one if you, well, on the x-axis, we have the distance between the nuclei, and on the y-axis, we have the potential energy. And the lower the energy, the more stable, right? So if you start from the right, when they're separate atoms, and then you move along as they get closer to the left, then you can see the dip as they start to form the bond. And when they get 0.074 nanometers apart, that's the perfect distance to balance those attractive and repulsive forces. If you try to get them any closer, then you go, and the potential energy goes way up, quick, really fast. And the point to make there is that if you try to push them too close, then you get those increasing repulsive forces, and now you're trying to move into nuclear reactions. So hydrogens, if you have enough energy in the system to drive those nuclei close together, like in the center of the sun, you have a lot of heat, a lot of pressure, you get them close enough together, then another force takes over. The strong nuclear force will bind those nuclei together, those protons together in a helium atom. And once they get that close together, then the strength of the attraction is just that dip, it goes back way down. And then the difference between the energy before and the energy after is expressed in a loss of mass. And when it loses that mass, you can convert that mass to energy with Einstein's equation. So the difference in mass between the two hydrogen atoms versus the one helium atom is an expression of how much energy you get out of that reaction. But that's not chemistry, right? Well, I guess they call it nuclear chemistry, but we're not going there. I just thought it was an interesting way to describe how high that energy is going as you get closer. Okay. Okay, ionic bonding. These are takeaways from our discussion. To have an ionic bond, electrons must be transferred, and then the opposite charges can attract one another. Covalent bonding requires that electrons be shared between the nuclei, usually because the atoms are close to each other on the periodic table. And when we speak of ionic bonding, we're saying metals and nonmetals. But covalent bonding, we're saying non-metal, non-metal. Okay. You may be wondering, well, what about the metal-metal? Well, that's a different class of bond, metal bonding. And we're not going to go there yet. We'll talk about it later. It's not quite as important to our understanding at this point. Now, intermediate cases where you get, say, the metal is really close to that zigzag line, and the non-metal is also close on its side. As you move from this element to that element, and then you move closer and closer and closer, what you're doing is you're increasing the ionic character of the bond. It may still be covalent, or it may be ionic. And as it gets closer, if it's ionic, then you increase the covalent character. So it's not really, it's this or that. It's kind of some of this and some of that. So every bond, with very few exceptions, has both ionic and covalent character. Now, if you want purely covalent, then both atoms must be identical elements, like two hydrogens, two oxygens, two nitrogens. Then you can say that's 100% covalent. All right. So when we talk about covalent bonds, we can also identify well, when we have two hydrogens, let's start there. Two hydrogens, we have an even distribution of electrons between them. Okay. But if this one happens to be a stronger attractor for electrons than this one does, and it's still covalent, but if this one's more strongly attracted, then we tend to get kind of a warped bond, right? Electrons, probability of finding electrons is concentrated more toward this side than the other side. In that case, then we start to develop a permanent slight negative charge. It's not a complete charge because we haven't completely transferred electrons. Right? So what we do is we identify this as this small delta, and this small delta gives it this partial negative versus positive, or sometimes we draw an arrow saying this is the positive side and that's the negative side. That's a designation of a polar covalent bond. Now, if there is equal sharing, like with this one, that's a nonpolar covalent bond. Right? That's purely nonpolar. There's no charge separation whatsoever. Whereas in a polar covalent bond, you do get some unequal sharing of electrons in that covalent bond. And since it results in a partial charge separation, then if we have nothing but XYs in this substance, then they will tend to orient themselves like this, right? With the positive side on this and the negative side on that. And you'll get an attraction between the two. Or if you put something else in there that's also polar or even ionic, then they will start to orient themselves so that they have positive, negative, positive, negative. Now we can quantify this polarity as long as we can put that compound in the gaseous state. Then we can put it between two plates that are oppositely charged and measure the effect that this polar covalent compound has on the charge between the plates. We can actually measure it. And that quantifies that polarity of the molecule. This one, I think, is hydrogen fluoride. Okay, what's meant by the term chemical bond? In general, it's a force that holds atoms together so that they function as a single unit. Now that's true for covalent bonds. Right? Water is covalently bonded, oxygen to two hydrogens. But when we talk about ionic bonds, we're talking about individual ions. So these don't function as a separate unit. In ionic bonded compounds, what you get is an array, a matrix. Let's move on down here. So we get a sodium here. And this, think of this in 3 dimensions also. It's into and out of the board. And it's just an array, a crystal matrix of positive and negative ions. Right? This just happens to be the simplest whole number ratio of the two. And we do it by balancing charges. If we tried to be brutally accurate, right, with this little crystal of sodium chloride, we would have to say Na to the 4.7 billion and Cl to the 4.7 billion, right? So we just take it to the simplest whole number ratio. Why do atoms bond with each other? Well, they form compounds because it's an energy advantage. The separated atoms have a higher energy state than the combined atoms. So there's an energy advantage there that the aggregate has over the individual reactants. How do they bond with each other? Well, they either transfer electrons, or they share electrons, or they're somewhere in between. Now, that concept I was talking about just a minute ago, where you have this uneven distribution, it can also be quantified. It's called electronegativity, and it was first proposed by Berzelius. in the early 19th century and studied by other chemists. Remember, Berzelius was the one that gave us symbols for our elements. He did a bunch of other stuff too. We used to use a tall beaker. In fact, we've used tall beakers too. Tall beakers like this, called the Berzelius beaker. He invented some glassware because it wasn't commercially available, so he just made it himself. Or he worked with somebody to make it. I'm not sure if he actually made it himself. I wouldn't be surprised if he actually made these things himself. Okay, so electronegativity has a very specific definition, and it's determined experimentally for covalently bonded compounds. Come on, here we go. And it tries to quantify and express the attractiveness of an atom to electrons. Now, the quantification of this value didn't come along till quite a bit later. Berzelius talked about it, and others studied it, but it wasn't until Linus Pauling proposed his quantitative approach for determining the electronegativity that we have a scale that we can apply to elements on the periodic table, and we can say there's a periodic trend with electronegativity. Yeah, that's one that we didn't discuss in chapter 7. So we're going to add that to our quiver. While we're here on Linus Pauling, he wrote a book. It was quite a bit before, couple of decades before. He got the Nobel Prize in 1954 for his research into the nature of the chemical bond. He wrote a book and tried to synthesize everything that we knew up to that point about the chemical bond. And it was so convincing that the Nobel Committee thought it was worth the prize. He also got a Peace Prize in '62. He was, as so many scientists were in those days, they were against nuclear proliferation. I mean, that's a noble pursuit, but once the genie's out of the bottle, there's not much you could do about it except go into Iran and bomb them into the Stone Age to keep them from getting nuclear weapons. Okay, so this was a rough approximation of the calculations that Pauling used. And focus your attention on if we're going to determine the electronegativity of X, then we'll form a compound with hydrogen, and we'll measure, like in those plates, we'll measure the measured attractive force between the two, and that'll be HX, that's the bond energy. And then we'll calculate the expected bond energy with that formula. Right, we'll say, all right, what's the bond energy between two hydrogen atoms? What's the bond energy between two X atoms? And we'll add those together and divide by 2. And that'll give us a theoretical value. Then we compare that theoretical value to the actual measured value and give us a relative approximation of the electronegativity of the X atom. Well, there we go. Oops, skipped one. Here we go. Too much delay. Did that one already. There we go. So this difference, the delta sign, is simply actual minus what we expect, and that gives us a value. If delta is 0, then there's no difference between hydrogen and the other one. They're the same. But if there is a difference, then that gives us a relative idea of how electronegative the X element is. I think they use hydrogen because in a bond, it's just a proton with its one electron out here. So that's as close as you can get to that other atom, is just one proton. If you tried to use something else, it would be more standoff. You can get really close with that hydrogen atom. And that takes the that little R value out of the equation. It's not as, actually, we shouldn't even be talking about that because that's ionic bonding. So on the periodic table, electronegativity increases from left to right in a period, and it decreases down a group. And so here's our periodic table. And let's see, we have about 6 of them this way, and about 10 of them this way, and then 2 over here. Okay, let's see, hydrogen's up here by itself, and helium's up here by itself. Okay. So, and we don't even think about noble gases in terms of electronegativity, because they generally don't form bonds. Some of the bigger ones have been forced to form bonds, but they don't form bond with hydrogen, so it's difficult to measure them, so we just kind of leave them out. So as we go from left to right, electronegativity increases. And as we go down, electronegativity decreases. Now we studied, say, ionization energy. Ionization energy increases from left to right also. And they're sort of related, because as we go from left to right in a period, you're increasing the number of protons without increasing electrons at a greater distance from the atom. So as we increase that number, we increase the nuclear charge as we go from left to right, there's a stronger attraction for electrons, either in the atom or outside the atom. Whereas when we're going down a period, down a group, we're adding protons and electrons in higher and higher shells, larger and larger shells, energy level shells. So you've got these electrons, the inner shells, the core, they're shielding the nuclear charge. So you don't feel as much nuclear charge out here as you do at this point. So taken all together, electronegativity increases from lower left to upper right. And the most electronegative, on the Pauling scale, the most electronegative is fluorine with 4.0. And the lowest is cesium or francium. They both about the same. Cesium's down here with 0.7. Okay. So if cesium and fluorine got together, that would be a very, very polar covalent bond. Actually, it wouldn't even be covalent. There's such a big difference, it would be ionic, no doubt about it. Now there's I think it's a chart coming up next. Not yet. This is a representation of the, trying to show you the differences in electronegativities as we go across the table. Notice that when we get into the transition elements, they kind of roller coaster. So the trend holds really well if you stay with the representative elements. Oops. So if lithium and fluorine react, which has more attraction for an electron? Well, fluorine, obviously. Anything with fluorine is going to lose. Okay. That's simply because their electronegativities are so different. In a bond between fluorine and iodine, the fluorine still has a greater attraction. So if we had fluorine and chlorine, bromine, iodine, iodine would be at a lower electronegativity than fluorine, but it would probably still be covalent. But the attraction of electrons to fluorine would polarize the bond. Okay, there's our general trend. And across the period, the number of protons increase. The effective nuclear charge is what accounts for the greater attraction for electrons. And down a group, as you're adding electrons and protons, you're adding electrons to bigger and bigger shells. Plus, you're shielding the nuclear charge with all those extra electrons. So that decreases its electronegativity overall. Now, this slide, at least the top part of the slide, came out of your textbook. I think I added the bottom part. If you take the difference, if you find two atoms that you want to say, all right, how do they bond? Then you subtract the smaller one from the larger one and see what the difference is. And if the difference is 0.2 or less, then this is definitely covalent and nonpolar. And those would have to be like very close over here. If you're between 0.3 and 1.4, and they're still from this area, then you can say they're polar covalent. But if it's a metal nonmetal, and the difference is, I think the difference is greater than one or greater, then you're going to say it's ionic. But if they're both nonmetals, then you can go down to 0.3 to 1.4 and say they're polar covalent. Anything over 1.5 or greater is ionic. And the only way you can get that is to have a metal and a nonmetal. Okay, let's see if we can arrange these range the following bonds from most to least polar. All right, the first one's easy. The first one should be relatively easy because you've got nitrogen bonded to fluorine, and you've got oxygen bonded to fluorine, and then you've got carbon bonded to fluorine. So to put them in order, the least polar would be which one of these is nitrogen, oxygen, or carbon closest to fluorine. All right. So it looks like oxygen is closest to fluorine, right? So that means this one would be the least. And the furthest away would be carbon, fluorine, and then nitrogen in the middle. So carbon, nitrogen, oxygen would be the best arrangement for this one. Okay. How about the second one? So if we've got carbon and fluorine and silicon and fluorine, and then nitrogen and oxygen. Nitrogen and oxygen are right next door. Right? So I think they would probably be the least polar. The greatest, the most polar, would be not carbon and fluorine, but silicon and fluorine. Because silicon and fluorine, carbon is in the same period. Silicon is in the next period. So it must be less electronegative than carbon. So I think that would be the best order. Okay. How about the next one? So if we're going to put them in order from most to least polar, right? The last one, chlorine and chlorine, is non-polar to the nth degree. If you want to include it in our thing, it's not even polar. So the other two we're dealing with are boron and chlorine, and sulfur and chlorine. Boron is way over here. Sulfur and chlorine, that's a tricky one. Right? Which one? I think that probably boron and fluorine is more polar, simply because of the distance between them. And then sulfur and fluorine should be in the middle. Chlorine, sorry. Chlorine. They're all with chlorine, aren't they? Yeah, sorry. Chlorine. Well, now it makes sense. Now that I look at the problem, sulfur and chlorine are right next door to each other. And boron and chlorine are different. There we go. So that's kind of using semi-quantitative. We know their relative positions in the table, we're just not given the numbers. If you're given the numbers, it's easy. You just see what's the difference and then put them in order. Which of the following bonds would be the least polar, yet still be polar covalent? All right. So let's see. I guess we can write over that. Still be polar covalent. All right, which one? Let's knock out the ones that are obviously ionic. Magnesium and oxygen. That's ionic, so we'll throw that one out. The least polar but still polar covalent, we throw out oxygen too, because it can't be polar at all. So actually carbon, silicon, and nitrogen. So carbon, silicon, and nitrogen with oxygen. Nitrogen with oxygen is probably the least polar. Yeah, because they're so close to each other. Okay, most polar will be without being ionic. So we still have to throw out magnesium and oxygen because they're ionic. So then we want to get the furthest apart. So since we're dealing with oxygen, we can go carbon is the furthest, silicon is the furthest away from oxygen. So silicon and oxygen should be the most polar. Oops. Now, why is that? Well, let's see. 3.5 minus 1.8. This is oxygen. This is silicon. 3.5, 1.8 is 1.7. Uh-oh, that's too big. That has to be ionic. Yeah. That's greater than 1.5. So we have to call it ionic. So that leaves carbon and oxygen as our best. Most polar without being ionic. Okay? Yeah, if we go back to that chart. Okay. When I drew that arrow on the bond, that is called a moment. In physics, we call it a moment. A moment just means it's an expression of a magnitude that is static. And a dipole moment is the magnitude for that bond. So there's a dipole moment, it's expressed this way. Okay. We use an arrow. Positive side is on this represents the positive side, and that represents the negative side. Two factors determine the dipole moment of any molecule. One, now we're going from individual bonds to whole molecules. Right? So we could have the water molecule like this, right? We would have a dipole moment toward the oxygen because it's more polar than hydrogen, like that. But what is it for the whole molecule? Well, first of all, in order to determine the dipole moment of a molecule, you have to have individual bond polarities. And we do here, right? If we had ozone, if we had ozone like that, then those bonds are not polar, right? So we can stop there. But if the bonds are polar, then we have to decide, is the molecule polar? And that depends on geometry. Okay. Geometry says here, and this, again, we're going back to physics. It's called vector addition. When you add two, and this moment expresses a vector of force in physics. So if we have this point, the static point, and we're pulling on it with this amount of force, but over here we're pulling on it with only this amount of force. What's we call it the resultant? What's the vector addition of these? Well, the best way to do it is to say, draw a parallel line here, same length as this one, then draw a parallel line here, same length as that one, and then this is the resultant. So these two pulling in their different directions adds up to the same effect as a single pull in that direction. And the length of the arrow represents the force. So this is more force than this one is. We can do the same thing for our molecules, right? If we have this force this way and we combine them, then we're going to have an overall dipole for the molecule in that direction. Okay? And that depends on geometry. Now, if we had say, carbon dioxide, and we'll prove this later. So that's the carbon dioxide molecule. This is going to be polar that way and polar this way. Same magnitude, opposite directions, right? So we got polar bonds, but they cancel one another out. So this molecule is non-polar overall. You still have the polarity of the bonds, right? So you're going to have, say, if we tried to represent electron density around this thing, we would do something like this, right? So you still have a slight accumulation of negatives on these ends, and then the positives in between. But overall, the molecule is considered nonpolar because those forces cancel out. So we got to find a way to determine the geometry of molecules, right? How did I know that water was bent? No, we're going to learn how to do that. Well, there it is. And it shows you the negative is redder and the positive is bluer. So you still get those uneven distributions. Actually, for this one, it's definitely polar. And that polarity is responsible for various physical and chemical behaviors of water. Like water boils at 100 degrees. If it were nonpolar, it would boil at maybe -50 or -60 Celsius. But that polarity gives it those bonds between the molecules that I talked about, those intermolecular bonds. And those hold it together until we put in enough energy, which is 100 degrees, to get it to vaporize. And there's your carbon dioxide. That's not drawn correctly because it only shows one bond between them, and it's actually a double bond. But we'll forgive, I guess. Okay, so here are representations of other types of geometries. Right? You can have linear geometry, like the top one, carbon dioxide. You can have a central atom with 3 around it. We always look for the central atom. Central atom in carbon dioxide is carbon. And the central atom in SO3 is sulfur with the oxygens around it. And that's a trigonal planar. That they're sitting in the same plane, but they form an equilateral triangle. If you draw a triangle around the molecule, that's what you get, an equilateral triangle. If we're looking at carbon tetrachloride or methane, we're going to get a tetrahedron. That's a regular arrangement of those atoms with carbon as the central atom. Okay, we'll come back to that in just a minute. What we've also noticed, and this is observed, once we learned how to draw electronic configurations, and we had an understanding for core versus, valence electrons, then we could look at, well, what happens when these atoms bond with one another to their electronic structure. Well, if we look at sodium, it has 11, right? Sodium has 1s, 2s, 2p, 4, 6, 3s1. Right, so that's 11. Chlorine has 17. So it would be 1s, 2s. We did do this already, didn't we? Okay. Sometimes I forget. 3s2, 3p, 5. So that's 10, 17. There we go. Okay. So what happens when we transfer an electron? Where's it coming from? It's coming from the highest energy shell, right? So we take this one electron and we put it here, right? So when we make an ion here, positive cation here and an anion there, we're actually changing the electronic structure. So this one disappears, right? There's no more electron there, and this one goes to 6. So what do you have? At the highest energy level for your electrons, you have an octet, right? At that valence level. Energy level 3, you have an octet. Now, sodium gave up an electron, but its highest energy level now is also an octet. And this is completely filled. The s orbital has 2 electrons, and the p's have 6. All paired up. It's a complete orbital. It's happy. Now this is related to a noble gas configuration. Chlorine now has 18 electrons and makes it look like argon. Sodium now only has 10 electrons and makes it look like neon. So they're tending toward noble gas configurations, at least for period 2 and 3, 1, 2, and 3. This is true. Now, when we get down to period 4 and above, you've got the d orbitals to mess with. And then the bonding is a little more complicated because you don't necessarily have an octet, and you can still form bonds. If we look at, let's look at an example. Let's look at 10. Okay. So 10 is here with 50. And we're going to use the abbreviated form. So we're going to go back to krypton at 36. And from krypton, we're going to 5s2, 4d10, and 5p2. Okay. Now these are in order of energy. But the position of the electrons is highest in the fives. So we're going to focus on fives. So if we lose these two electrons, which are higher energy than the S's, right? If we lose those two, that gives us a +2 charge, right? But if we lose the next two, right, now we have a complete 4D and we have a +4 charge. So that's where the preferred cation charges for tin are 2 and 4. And if you look at your periodic table, it has those numbers in the little square. Tin should have a +2 and a +4. That's where it comes from. And we can do the same thing for anybody in the group with tin. Like come down one more to lead. It just uses different numbers here. Like this would be 5 and this would be 6. But you can still get +2 for lead or +4 for lead. Or if you go to bismuth, right, which is to the right of lead, now you've got 3 electrons in the 6p. So we remove those 3 and make a +3, or we remove these 6 S2s and make a +5. So bismuth prefers 3+ or 5+. And thallium, which is below indium, to the left of tin, actually to the left of lead, it only has 1 in its p orbital. So if you lose that one, you get a +1. If you lose the other 2 here, you get a +3. What we're trying to do there is explain why with these higher, with the 4th and above periods, you get multiple possible charges. Okay, when two nonmetals react to form a covalent bond, they share electrons in a way that completes their valence configurations. And that's absolutely true with periods 1, 2, and 3. And it's a little, we have some wiggle room with 4, 5, 6, and higher. When a nonmetal and a representative group metal react to form binary ionic compound, the ions form so that the valence electron configuration of the nonmetal achieves noble gas configuration and also for the metal. The valence orbitals of the metal are emptied, and we add those electrons to the nonmetal, just like we did with sodium and chlorine as an example. What's an isoelectronic series? Well, the easiest one to visualize is where we have a noble gas in the series. Then all you have to do is for the other elements in the series is just add or subtract electrons to make them look like the noble gas. Then you have an isoelectronic series, which just means that they have the same electronic configuration. Right? So if there's the noble gas in there, then the others are going to be ions, and they're going to have the same number of electrons as the noble gas. And we see that if we start with neon, right? If we go this way, fluorine -1, oxygen -2, is nitrogen there? No. Or we could go the other direction, right? We go down here to sodium, it loses 1, makes it look like neon. Magnesium loses 1, makes it look like neon. Is aluminum there? Yeah, aluminum would lose 3 to bring it back to neon. But technically, isoelectronic series can also be all ions. You just have 1, and the rest of them become ions, or they could be elements, neutral elements, as long as they have the same number of electrons in their configuration. But we typically focus on the noble gases. That makes more sense if we're talking about bonding. All right, here's another example. If we start with argon, chlorine, we would go back and add an electron to get the argon. Or we go potassium loses one, calcium loses one, two, and that would look like argon. So I think what that's trying to point out also is why at the beginning we memorize charges for groups. Like the alkaline metals are always +1, the alkaline earths are always +2, boron, aluminum, gallium, indium are always +3, halogens are -1, chalcogens are -2, pnictogens are -3. For this reason, because that's where they're happiest. Okay, and the electronic configuration for each one of those is the same as argon. Number of electrons are going to be the same as argon. Number of protons stays the same as the neutral atom. Because if you change the protons, remember, you get a new element. Can't change the protons. Okay. We've looked at trends in chapter 7, atomic size. Ion radius, we sort of touched on that. Ionization energy, yes. Electronegativity, we covered that in this chapter. We looked at electronic configurations, prediction for ionic compounds, covalent bond polarity ranking, we've done that. So what are the factors that influence the stability and the structure of binary ionic compounds? Right. We can look at it another way. If we want to assess the amount of energy lost in the formation of a compound, we can look at this term called lattice energy. And this is applicable to ionic compounds only, lattice energy. We have to define it. Remember how we defined ionization energy? We had some atom and it was neutral gas, and then we added energy to it and we got a single positive charge plus an electron. So we use a similar idea for lattice energy. Come on. We start with separated gaseous ions. So let's use our old familiar. This is a gas, and this is a gas. It comes together to make that solid, right? And it's going to give up energy, right? So the energy change here is going to be negative. Here, we had to put energy in to get the ionization energy. So this change in energy was positive. That was an endothermic process. This is exothermic. This is the lattice energy. And it gives us a way to objectively rank the strength of bonds between cations and anions in an ionic compound. That's the main purpose for. And lattice energy can be expressed by using Coulomb's law, only the K varies. We do have an interest here in the size of the charges and the distance between them. So if the size of the charge differences increase, we get a higher lattice energy. If the distance decreases, we also get a higher lattice energy. Okay. Now, if we're going to form an ionic solid from neutral elements, there are several steps that we encounter in this process. And this is kind of a thought problem. In other words, there are ways to measure these values, but when you actually put the elements together, like magnesium with chlorine, put them together, and you have to kick them a little bit with some energy to get them started. Or magnesium and oxygen, that's a good one. Right? Have you ever seen the old light bulbs? Some of them times they're blue and they have these little fibers in them. That's magnesium. And inside that bulb is also oxygen, but it's relatively stable until you jolt it with an electric from a battery. And when you do that, you get an instant reaction between magnesium and oxygen that gives off a lot of energy in form of light. And that's how we used to flash photograph. Before we had those electronic discharge lights that could just flash over and over and over again. So you had a flash bulb, use it once, pull it out, throw it away. But this was the chemistry. Magnesium and oxygen combined give off a lot of energy. Sometimes in my classes, I'll take a strip of magnesium and hold it with a pair of tongs and light it. And you don't want to stare at it because it produces ultraviolet light. Anyway, when we're forming the energy of formation, if we were to take, say, magnesium metal, let's see, yeah, and say our oxygen gas, like that, and it's going to form magnesium oxide solid. So we need 2 oxygens and 2 magnesiums. So there's a certain amount of energy that's given off here, right? It's a huge negative energy discharge. That would be the energy of formation. Right? So we would have an enthalpy of formation for that process. Well, we break it down into steps. And we're going to focus on the metal first. So we take the metal, and the first thing you have to do is add energy to it. Right? Add energy to that and make it into a gas. Right? So this is an energy input that's positive. It's an endothermic process. Then you have to take the metal, this gas atom here, gas, and add energy to it, turn it into and this is ionization energy, right? Turn it into, well, actually, in our example here, they're just using the M for a metal. In our case, we would have to do 2 pluses, right? So this will be a combination of first and second ionization energy. Right? You would probably do 2 steps. Right? Take it to 1 plus and then take it to 2 pluses. So this is solid to gas. This is sublimation. Right? This is ionization. Okay. Now that we've got the magnesium 2 plus, we can focus on the nonmetal side. So we would take this oxygen and we say, how much energy does it take to form 1 oxygen atom in the gaseous state? Right? So we would only need half of this gas. Right? And this would also be an endothermic process for dissociation, or we'd have to break the bond. The amount of energy here is actually put energy in to break the bond, but you only need half of it. So this value would be half of that dissociation energy. And then we're going to take this one right here, and we're going to allow it to attract electrons. Right. So in our cases, we need 2 electrons. And this would be ionization energy, electron affinity. Electron affinity. But this is actually be 2 electron affinities, right? The first electron and then the second electron. would give us a value for this one. And then we would take these two, this magnesium 2 plus gas plus this O2 minus gas, and it would form magnesium oxide solid. And this is your lattice energy. And this is extremely, let's see, this is exothermic. Electrons coming from infinity to the atom is exothermic. And this was extremely exothermic. Okay, so this is the thought problem, how we think things happen. Now, when these two get together in this reaction, this all happens almost simultaneously. It happens so quick that I don't know of any instrumentation that can separate them. Maybe some scientist has used lasers to pick out each step. This particular diagram shows two reactions. Okay. The smaller reaction on the right, the bigger reaction on the left is this one, magnesium and oxygen. And the overall energy change is this positive, this positive, this positive, these two negatives, and they add together to give you that value. All these added together gives you that value. All these enthalpy changes added together give you that value. And that value for this reaction is minus 602. Delta H for this reaction is minus 602. I think it's kilojoules. Kilojoules per mole. Okay. But the other one, where we have sodium and fluorine, we have different absolute values involved, but the second one is not far away from the first one. It just made smaller jumps through these steps. Okay, 570 instead of 602. All right, so what accounts for the differences? Well, if we look at sodium and fluorine, sodium and fluorine produce sodium fluoride. These magnesium is definitely a well, you know, trying to think of the difference in size between the magnesium ion here and the sodium ion, Na plus, because they're in the same energy level. You've got one more proton in the magnesium, and you're removing 2 electrons. So sodium and magnesium, when they're ionized, still have 1s, 2s, 2p6, 1s2, 2s2, 2p6. But sodium only has 11 protons, magnesium has 12. So you got the same number of electrons in the same orbitals, but you got 1 extra positive. So this is probably a smaller ion than that one. But it's a higher charge. So if it's a smaller ion with a higher charge, it can get closer to its anion, and with a larger charge difference between +2 and -2, that would account for the difference in overall energies formation versus sodium fluoride. Okay. We can do the same logic for oxygen versus fluorine, but in the opposite direction, actually. Okay, so if we use the same sequence of events for lithium and fluorine, yeah, lithium and fluorine are in the same period, then we would sublimate the solid to a gas. We would ionize the lithium to a +2. That takes energy. Then we would go to the, now that we have it in the ionic form, we would go to the fluorine and we'd split that bond. That takes energy. We put energy in. And then we ionize the fluorine gas with a certain amount of energy. No, we don't put energy in. We get energy back because fluorine is attracting an electron. So that's why it's negative. Then we put the lithium and the fluorine ions together with our lattice energy, and we get that much energy back. Then we just add them all together. And the overall then is minus 617, even bigger than magnesium and oxygen. Now, since lithium and fluorine are both singly charged, and these were doubly charged, the difference between them must be that the lithium and fluorine can get much closer. Okay. Let's see. So we mentioned this a little earlier. No bonds, it says no bonds reach 100% ionic character. Even if they're considered totally ionic, they still have some covalent character. And I think you're going to find what that means is between the two atoms, even if they're ionic, you're going to find an increased density of electrons between the two than you would if they were separate. It may not be much, but it's measurable. And we can calculate the ionic character of the bond simply by measuring their dipoles. We can calculate the dipole for the two ions, and then we can measure the dipole in between those two plates and ratio them. And that gives us the percent ionic character of the bond. If we do that for these different compounds, we find that the ones in blue would be considered covalent, and the ones in red are considered ionic. Oops, went too far. Now, there's also an operational definition for ionic compounds, especially if you can get them in solution. Now, they don't necessarily have to be in solution. I mean, if you have an ionic compound that won't go into aqueous solution, in other words, when we have two solutions we mix together and it makes an ionic precipitate, right? They don't like aqueous solution. Then you'd have to melt it and free up the ions so they can move. But typically speaking, we're talking about compounds that go into aqueous solution. If they do that, and then the solution will conduct electricity, right? Put two electrodes in, battery and a light, and then maybe a meter, then you get the circuit. And if conduct electricity, that's also called an ionic compound. All right. So now we're going to try to explain with a model, which means whenever you see the term model as describing a process in physics or chemistry or any of the sciences, think theory. Models are always associated with theories, which means they're trying to explain why something happens. So when we got a theory and we have a model associated with it, This model could be a physical model, like if you had a molecular model kit where you could put balls together with sticks. You could form a model of a compound or a molecule and see what it looked like. That'd be a physical model. Or if you made a model airplane or a model ship, that would be a physical model. Models don't have to be physical in our world. They can be mathematical. And very often we treat them statistically. So we have statistical models that go along with the data set. But the first rule is models do not equal reality. Just because you have something that looks familiar doesn't mean that that's the real world. It's our interpretation of the real world so that we can try to understand how it works. It's a macroscopic representation, so to speak, of reality. Models are always oversimplifications. We only put the major factors into a model that we think influence its behavior. And they're often wrong. Models become more complicated or modified as they age, usually. Have I shown you what you do when a theory crashes? I think I showed you that earlier. What happens when a theory fails? Theory fails. You have options. The first option here is modify it. Right? Modify the theory, which means your model will change. Okay, to make it fit the data. And that's perfectly legitimate. They tend over time to get more complicated. Right? Time, complex. It's just the nature of the beast. Okay. Other thing you can do is restrict its application. Right. So the example I use is physics. Right. Newtonian physics. Those that obey Newton's laws happen within this range of masses. If you go too big, like toward neutron stars and black holes, then you have to go to relativity. And sometimes you even have to go to relativity for our sun. But you restrict its application. If it goes too small, then you go to quantum mechanics. Right? Or you can throw it out. Throw it out, start over. Okay. That was with the atomic model. Rutherford showed that the atom was, we did talk about that, didn't we? Rutherford showed that the atom was nuclear. It had a very dense nucleus and these electrons out here. Before then, the plum pudding model was accepted, right? When Rutherford came along and did his experiment, the plum pudding model was in the trash can. Right? And then the last one, which you won't see anywhere in any textbook, is you turn your theory into a religion. You just believe it because you believe it. Now, there may be reasons for you to do that, like if your career depends on it, right? If your funding comes from a government agency or some granting agency that says, we want research on this project, and you know the project is bogus, you may do it anyway. So you have to believe it. You have to turn it into a religion in order to proceed. Examples, right? Darwinism, right? Succession of species. Another is, I'll use the big term, anthropogenic. Climate change. That is, man causes the climate to change by his industrial activities. That's completely debunked, but there are people that still believe it. And there's usually lots of money associated with it. Okay, so back to our model. They become more complicated over time, usually. You have to understand that the underlying assumptions in a model so that we don't misuse them. Assumptions are not bad. It's the misuse of the assumptions to obtain a preconceived outcome. If you misuse your assumptions to get the outcome you want, then you're a bad scientist. That's all there is to it. When a model is wrong, we often learn much more than when it's right. Okay. So it's like Edison, when a reporter asked him how many times he failed to make a light bulb, he says, I didn't fail. I figured out how to make a light bulb, but these other 99 times just showed me how you can't make a light bulb. Right? It's a perspective. Okay. And, oh, I forgot I had this slide in here. Did I not show this to you guys earlier? Well, there it is again. Restrict its use, right? And I used Newton's laws as an example. Modify the model for new conditions, right? Some physicists believe that there are actually 26 dimensions in the universe, in the real world, not just length, width, depth, and time. And they have to do it mathematically, of course, because you can't see 26 dimensions here. I only see 3 physical dimensions and 1 time factor. Or you can form a singing group and call it 5th dimension. Throw the model out and start over. Yep. Or turn, and that example I used was the plum pudding model for the atom. I didn't throw religion into that one. Okay. It is true, nevertheless. Darwin wrote a letter to a friend one time after he published his Origin of Species. I think it was maybe the second publication, second printing. And he wrote a letter to a friend and said, if we don't find in the fossil record a very small incremental changes of fossils through to another species, he says, then my theory is bogus. He says, it will not hold scientific scrutiny. If we don't find that in the fossil record, we never have found it. Right? So that tells me that Darwin wouldn't even accept his own theory nowadays. Okay, bond energies. To break bonds, you add energy. That's just the way it is. The bond is more stable than separate atoms. So you have to add energy to get them apart. Right? That's breaking bonds, you add energy. So the energy value will be positive. You're adding energy to the system. If a bond forms, then it's exothermic and you release energy and the value will have a negative sign. Okay, we represent different types of bonds, single bonds, double bonds, triple bonds, as 2 electrons. So if we have, let's say, let's use water again. If we, instead of using the lines, we use electrons, right? We have that, then we'd have lone pairs. Right? These are bonding pairs of electrons, and a single bond is always 2 electrons. And it's represented by a single straight line. Lone pairs or non-bonding pairs do not occur between atoms. So you'll see them sitting off here by themselves. Those are, so if you look at this atom the way it is, that's 2, 4, 6, 8. Oxygen thinks it has 8, right? Thinks it has an octet. Hydrogen, of course, doesn't have room for an octet. It's only a duet. So it thinks it has 2. Okay, double bonds. If you have, if you have carbon and 2 oxygens over here, then we're going to have two pair, like that. And then we'll have, let's see. Yeah, then we'll have two lone pairs here and here and here. Yeah, so that's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So each atom thinks it has an octet. And then we would draw it like this, each line representing two electrons, and then our lone pairs. And then triple bond between nitrogen atoms. Well, let's do it this way. Be consistent. Like that. Now, 6 plus 2 is 8. 6 plus 2 is 8. Each nitrogen thinks it has an octet. And then we would represent it with 3 lines and the lone pairs. Okay? One thing we notice is as we increase the number of bonds between the atoms, the length of the bond decreases. It's an indication of a stronger bond. So the bond strength increases and the bond distance decreases. It's not linear. In other words, the double bond is not half as short as the single bond. And the triple bond is not a third as short as the single bond. Right? It is shorter, but it's not linear. And eventually we'll show you why that is. All right. Let me see if somebody's tried to contact me. No. No. Focus messages. No. Okay. Through numerous experiments and dozens of scientists working on individual projects, we've compiled a list of the energies of bonds. So the hydrogen-hydrogen bond is listed at 432, and the units aren't given, so I think it's kilojoules. Kilojoules per mole of those bonds. All right. What that means, since these are all positive values, that means that is the amount of energy required to break Avogadro's number of hydrogen-hydrogen bonds. That's the way you interpret it. So if we went across to the nitrogen-nitrogen triple bond over there on the right, third from the bottom, 941 kilojoules. Right. If we look at the nitrogen, let's see, do we have a nitrogen-nitrogen single bond? Yeah. Second one from the top in the second column, 160. So that's 160 for this one. Kilojoules. Whereas the triple bond is 941. You know, I messes with my my previous statements. If we took 3 times this one, that would be 480, right? Like, this is a lot bigger than that. Well, I can still stand by it's not linear. But the strength of that bond is a good indication of why nitrogen is so stable. It's a very stable molecule. It's almost inert in our atmosphere. We can breathe the nitrogen in and it dissolves in your tissues, but it doesn't react. Not like oxygen does. And that's why food manufacturers, they used to, let's take potato chips for an example. Right? One thing that potato chips do, since they're cooked in oil, is over time they'll go stale, and then if you give them enough time, they'll go rancid. when oxygen reacts with the oils, it produces acidic and compounds and aldehydes, and it's nasty. It's not a product that you'll be able to sell. So originally what we did was we added compounds to the potato chips that would scavenge oxygen from the air. And in a closed environment, they would scavenge that oxygen and it wouldn't be available to destroy the oils that were in your potato chips. But those compounds, some of them were identified as carcinogens, or at least unhealthy in prolonged exposure. So they went to putting the compounds impregnating the packaging material with the compounds. And that gave less exposure to the consumer. But that didn't go over too well either. So the next idea, which is what they do now, is as the potato chips are being packaged, they blow nitrogen into the bag and expel all the oxygen and then seal it up. So that's why the bags are puffy. They're under positive nitrogen pressure inside. And that nitrogen will not react with the oils, and it expels all the oxygen. So it keeps them fresh until you open the bag. Right? And then usually the bag doesn't last long enough to go rancid anyway, especially if they're Lay's. And that's also why it takes a special enzyme system to take nitrogen from the air and fix it in a form that plants and animals can use. Right? Because nitrogen is the basis for amino acids, right? Proteins, and nucleic acids. You have to get nitrogen in a reduced form, we say. And that takes a special enzyme system that's only present in certain bacteria. For legumes like clover and alfalfa and soybeans, the nitrogen gets into the soil, and these bacteria and nodules on the roots. If you pull up a soybean plant or even a clover plant, you see these little knots on the roofs. That's where those bacteria live. And if they're pink, they're active. And they take nitrogen from the air and they fix it into, usually they go to ammonia first and then they go to nitrates. And that makes it available for the plant. So the plant provides them with some energy from the sun, and they use that in their enzyme system to break the bonds with nitrogen and form bonds with hydrogen and oxygen and make these available compounds. But the strength of that bond is the real problem. It takes an enzyme to do that. Well, actually, you can do it with a catalyst. Haber, Fritz Haber, took nitrogen and used iron catalyst at elevated temperatures and pressures to form ammonia from nitrogen. And it took huge amounts of energy to do it. Legumes do it at ambient temperatures with their enzyme systems. Okay, that's enough of that. So, just to reiterate, when we have a bond, energy must be added to the system in order to break the bonds. It's endothermic. And if a bond forms, energy is released. That's an exothermic process. We can calculate the change in enthalpy for a given reaction if we know the bonds that are being broken and formed. So we take that energy and we say, all right, we add up all the energy that it takes to break the bonds, and then we subtract the energy values for the energy released. And the reason we do it in that order, rather than the bonds formed minus the bonds broken, which would normally be the way you do it, the final minus initial, we do it this way because all the bond values are positive. Right? So the positive ones are the ones broken. We have to put that positive energy in. And then we subtract the energy for the bonds that are formed. And since they're positive values, the energy released, we have to put that negative sign in there to make it come out right. So if we know the reaction and we know the bonds, the total bonds, then we can add up all the energies for the reactant side and subtract the energies for the product side and come out with an enthalpy for the overall reaction. And it's really pretty accurate. Right? For this example, we have I'm not even going to try to name those compounds. Notice the difference between the two. The CH3 is the same on both sides. And when we write organic compounds like this, CH3, the first one is N, right? What that means is this carbon is bound to that nitrogen, and these hydrogens are bound to the carbon. Right? That's convention for organic compounds. The hydrogens are not bound to the next compound, they're bound to the carbon. Okay, because hydrogens can only have one bond anyway, so they couldn't be bound between these two. Okay, the difference you see there is between the triple bond of nitrogen and carbon is flipped on either side. So on this side, that nitrogen is bound to the carbon like this, but on this side, we have the same bonds here, and this side we have a carbon and then a triple to nitrogen. So the only difference between these two is that bond right there. So if we have the enthalpy for this CN bond and we subtract the enthalpy for the CC bond, we should get the answer. Okay. So the CN bond is 305. And then the CC bond is 347, minus 347. Right? So that's negative 42 kilojoules per mole. Now we could have gone through and added up all of the bonds, which is the way the formula says, but it would be the same on both sides, so they cancel out anyway. We want the ones that are different. Right? So it's 42 kilojoules for this reaction. Coming up on 2:30. Let me see, where am I? Okay. This is where I sometimes pause. If I need, if the classes are kind of out of sync with the labs and I need to do 2 periods, this is where I break it. But since we have lab time available, I'm going to go ahead. And the reason I break it there is now we're going to get into a useful theory for the explanation of bonding, the valence bond theory. The valence bond theory, and it has an associated, it has actually more than one model associated with it. The valence bond theory says that atoms bond with each other by overlapping their valence electrons, or the orbitals that are occupied by their valence electrons. They just overlap. The electrons still belong to each of the atoms, they just share them. Right? So we don't even consider those core electrons. We just focus on the valence electrons. And for many years, this was perfectly adequate. The problem is, in the picture form, it explains something about the bonds, but it says nothing about the energies. It has no way of saying what the energies are. Right? And that's, to chemists, to scientists, that's taboo. You got to know energies to say anything substantial about any type of process. But this is where we're starting, the valence bond theory. So we have a model, this localized electron model, says that the molecule is composed of atoms that are bound together by sharing electrons between atoms. So we focus on individual bonds. And the model itself was incorporated, or I don't know if it was incorporated, it came out of the quantum mechanical model of the atom. It's an extension of the quantum mechanical model of the atom. So electron pairs are assumed to be localized on a particular atom or in the space between two atoms. That's essential for this localized model. So we'll have lone pairs, like on our oxygen, we had two lone pairs on the water molecule. And then we had a bonding pair between oxygen and hydrogen, and another bonding pair between oxygen and hydrogen. Those are defined relative to the atoms that are being bonded, or the atom that retains total possession of its valence electrons. So oxygen shares a couple of electrons, and it also keeps 4 of them as lone pairs. So here's what we're going to do. Item 2 and 3, part 1 and 2, we're going to do today. And then we're going to get into part 3 in chapter 9. So you don't have to worry about part 3 yet. Okay, that brings us up to the beginning of the 20th century. Linus Pauling was active, and another brilliant chemist, G.N. Lewis, was also active, working with covalent bonding. And he also described how the configurations, the electronic configurations of atoms in a bonded group are approximating or trying to emulate noble gas configurations. So when he got that idea in terms of the octet, he focused on the octet. He came up with a way of representing these atoms so that we could visually look at them and move them around for a reaction to occur, and end up with something that was reasonable based upon the experimental data. Now for hydrogen, right, it doesn't have an octet. It only has one s, so it only has 2 electrons available to look like helium. So this is the duet rule for hydrogen, and it's the only one that obeys that. The rest of them are octets. Okay, so fluorine, this is called a space-filling model. Single covalent bond, double and triple covalent bonds, we talked about those already. And then, I want to be sure I didn't skip a slide. Okay. G.N. Lewis came up with this system. It's called the Lewis dot system, or Lewis dot structures, I like to call them. And what it does was it uses the symbol of each of the elements, say fluorine. Right? Fluorine has 9 electrons, and if we drew out this electronic configuration, we would have 1s2, 2s2, 2p5, right? 5, or it's 9. We're only interested in the valence shell, right? So Lewis said, all right, let's take those 7 electrons and let's place them around the symbol. 1, 2, 3, 4, 5, 6, 7. Those are the electrons available for bonding. Valence bond theory, those are the valence electrons. And if it comes close to some other atom, and we can arrange the electrons in that so that the bond gives each one of them a duet or an octet, then we've got a valid proposition for a compound to form, or at least a bond to form. If we use just hydrogen, of course, hydrogen has this one electron. If these two share, now we have that. And that's the Lewis dot structure for hydrogen fluoride. Actually, it's usually reversed. Now, when we're given a formula for a compound, and we're trying to put the atoms in the proper order, unless you're told otherwise, you place the more electronegative atoms near the center of the group. They are the central atom before we position the other atoms around them. And sometimes you can propose more than one structure. So we've got to decide how to tie break, which would be the best Lewis structure. And we're going to talk about that too. For instance, if we have, let's see, carbon tetrachloride. We know that's a valid formula for carbon tetrachloride, right? So this would be an exception because this carbon is less electronegative than the chlorine, but we do put it in the center, right? And then we form bonds with the chlorine atoms. But suppose we have let's see, IF5, say. Well, that didn't work either. I'm just digging the hole deeper. Let's move on, and if we have to make a choice, then I'll show you how it's done. So here's how you write the Lewis structure for any given atom or a molecule. Right? Atoms are easy. You just take the valence electrons and position them. Molecules, we need a set of instructions. Right? So if we have water in this case, you add up all the valence electrons. So hydrogen has 2, and oxygen has 6. Right? It has 8 total, but only 6 valence. Right? And if you count from the left, lithium, beryllium, boron, carbon, nitrogen, oxygen, 6 electrons, 6 valence electrons. Add them all up, that's 8 electrons. Then you put the more electronegative, in this case, obviously, oxygen is more electronegative, put it in the center. There, and draw a single bond from it to the other atoms. So we got one single bond to hydrogen and another single bond to hydrogen. That's 4 electrons. Subtract those from 8, and that shows you how many you have left to deal with. Okay? And then you position the electrons where they can produce an octet. Hydrogen doesn't need any more. It has its duet, right? It has 2 here and 2 here. So you move from the outside and work your way in. Okay, in means that we have 4 electrons left. So you put 1, 2, 3. And then you say 2, 4, 6, 8. We've used them all up. So we've positioned our electrons correctly. Now, that's a valid Lewis dot structure. It doesn't incorporate the geometry yet. But this is where we start. We have to do this before we can go to geometry. How about PBr3? Okay, we're going to put phosphorus in the middle. But first we're going to add up the valence electrons. Phosphorus has 5. Right? It's 5 from the left. So it's 5 electrons. Bromine has 7 times 3. 21 is 26 electrons, right? Okay. So we put the phosphorus in the middle. And then we position our 3 bromines. Okay. 246. That means we have 20 electrons left. Work from the outside in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Is that right? Hold on a second. I got a better way. Foolproof. We're trying to make an octet around bromine, right? Each bromine already has 2, so it needs 6 more. So if we put 2, 4, 6, 2, 4, 6, and 2, 4, 6, that's 3 times 6 is 18. And we have 2 electrons left over. Now that you have an octet here, we have to move in. So now that lone pair goes on there. Phosphorus. But phosphorus, if we can, we need to make an octet for phosphorus too. So we're going to take this lone pair and we're going to make a double bond. So that means 2, 4, 6, 8. 2, 4, 6. Oh, I'm sorry. That won't work either. Because bromine already has 8. So that's it. That's it. We can't make a double bond anywhere because bromines already have 8. So now we have 6 bonding pairs around phosphorus and 1 non-bonding or lone pair. Yeah, there we go. How about HCN? Hydrogen cyanide. Okay, we have 1 electron there, we have 4 there, we have 5 there. Right? Yep, 5. So that's 10 electrons. So we're going to put carbon in the middle. And usually, excluding hydrogen, if you need to find a central atom, you go to the left. Which one's furthest to the left? Right. That's carbon. And then we have 1 bond here, 1 bond there. So that's 2, 4. That's equal to 6 electrons left. So we 2, 4, 6, because we're working outside in until we get an octet. Now we got to make an octet for carbon. The only way to do that is to make a bond between that and nitrogen so that nitrogen doesn't lose. So there's 1 pair, there's the other pair. Now we have 2, 4, 6, 8, 2, 4, 6, 8, and 2. So that's a Lewis dot structure for hydrogen cyanide. Takes practice. But it's very useful. Okay. Come on. Oh, now how do we know that? Okay. That's where we get into another model. Lewis dot structures for these guys. I don't want to do those. Let's do ammonia. I've already shown you carbon dioxide. So let's do ammonia. That's a new one. We have NH3. So nitrogen is 5, and that's 1 each times 3 is 8 electrons. Nitrogen central, and we have 1, 2, 3 hydrogens. That's 6, and we have 2 left over. So there's your Lewis dot structure for ammonia. And we don't have to make any other bonds because hydrogens have their duets, nitrogen has its octet. Now, sometimes the octet rule comes up short. We run out of electrons. This boron trihydride. Now, first of all, we have to know that that's a valid compound. Yeah, It's been isolated, characterized, it's real. Right, so we know the bonds are there. So boron has 3, and then 1 each for this one is 6 electrons. Okay, so boron in the center, 1, 2, 3. That's it. We've used them all up. So what we have is a problem with an incomplete octet for boron. The other possibility is exceeds an octet. So our examples here are sulfur tetrafluoride with 34 electrons. And we find that we make single bonds with the fluorines. They all have octets, but the sulfur has to take on an extra pair. Right? So it has an octet, actually has 10 electrons around the sulfur. And arsenic is another possibility. Arsenic pentabromide has 10 electrons around it. They're all in bonds. So how do we explain that? Well, look where sulfur and arsenic are. Sulfur's in the 3rd period, arsenic's in the 4th period. So what do we have available to us? Right, we have 1s, we have 2s, 3s, 4s. We also have 2p here. We have 3p here, but we also have 3d there. And here we have 4p, 3d, 4d, 4d, and 4f. So for sulfur, here, it has available 3ds. And that's where that extra pair goes. It goes into a d orbital. For arsenic, we're down here. And arsenic, it has available to it, let's see, we're filling this up. Now we have the 4d available to form a bond. Only when you have those d orbitals available can you exceed the octet. For the 2nd period, you never exceed the octet. You may come up short like boron does, but you won't exceed it because you don't have access to d orbitals. Okay, there's BF3. What we had to do with BF3 was make a double bond. So that would give boron an octet. So in this case, boron trifluoride still obeys the octet rule. Phosphorus pentachloride exceeds the octet. And sulfur hexafluoride definitely exceeds it. It has 4 extra electrons in bonds. Okay. These are just summarizing things. Boron and beryllium, sometimes they come up short. Carbon, nitrogen, oxygen, and fluorine always obey the octet rule. And 2nd row elements never exceed 3rd row elements, or heavier ones can exceed the octet rule if necessary by using d orbitals. There we go. Try to satisfy the octet rule first with the available electrons. And then if you have to, form bonds as long as the bonds don't cause any other atom to, if it already has an octet, you use some of its electrons, form a bond that will preserve its octet. Now here's another problem. Valid Lewis structures can be multiples. Right, so this nitrate, we drew the nitrate, right, we would have the potential for like that. That would be a possible nitrate. And don't forget the charge, because that's an extra electron, right? We would have 5, and 3 times 6 is 18 plus 1. So that's 24 electrons, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons. You have to have that negative there. But who's to say that we form the double bond on this side, right? Because all these oxygens are equivalent. So maybe we form the double bond on the other side, right? Like this one. Or we could form the double bond over here. So there's a problem with the theory, and the model is being difficult, right? So what do? Well, we modify in this case. We introduce the concept of resonance. So the structure is not only one of these, it's all three. And they resonate so fast that we can't tell them apart. Now, we have been able to measure the bond length, bond strength of this nitrogen oxygen. They're all equal. They're all the same length. All right, so that means that we could draw it this way. Let's see, there, and oxygen, oxygen, oxygen. Let's see. Like that. The problem with that is, where do you put the other electrons, right? Because this way, you've identified where the electrons are located. But this way, you say there's kind of smeared out. So we can't actually say where are the lone pairs. You know, it won't work. So that's not a really good approximation either. So that's one problem that we solved by resonance. That was proposed by Linus Pauling. These electrons are said to be delocalized. Now, the one advantage to thinking of electrons as delocalizing in a molecule is delocalization lowers the energy and stabilizes the molecule. So that's one advantage to representing them this way. This resonance delocalized electron density over the molecule in 3 bonds instead of trying to put a double bond here and there and there. So that does stabilize the molecule, this delocalization. All right. Do we want to draw, let's see, how about, pick one. We've done carbon dioxide already. Carbon monoxide, we could do that one. Okay. So this is 4 and this is 6, right? 10 electrons. So carbon, oxygen. So let's do that. Means we have 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 2, 4, 6, 8, 10. That's all of them. Okay. So how do we make an octet here? Well, notice we have incompletes here. Right? So if we take these two and make a bond, take these two and make a bond, then we get a triple bond with a lone pair here and a lone pair there. Now, is that a polar molecule? Probably, slightly polar. How about methanol, CH3OH? Okay, so this is going to be 4, and 3 times 1 is 3, and 6 and 1. So that's 14 electrons. So this is going to have 2 centers. It's going to have a carbon here and then it's going to have an oxygen there, and then a hydrogen here, and 3 hydrogens here. Okay, 2, 4, 6, 8, 10. 4 electrons left over. Well, carbon's already got an octet, and hydrogen can't hold anymore, so these 4 electrons have to go on the oxygen. So that's 2, 4, 6, 8, 2, 4, 6. Let's see. 2, 4, 6, 8, 2, 2, 2, 2, 2. So there's your methanol. How about OCN minus? The way that's written, that tells me that carbon needs to go in the middle. So let's see, this is 6, 4, and 5, and 1. So that's 16 electrons. So we have an oxygen on this side and a nitrogen on this side. All right, so that's minus 4 is 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Use them all up. But carbon doesn't have an octet yet. So which would be the most likely? Well, my first choice would be make a double bond on this side and make a double bond on that side. That's a possibility. The other possibility is to leave this oxygen alone, since it's electronegative, and make a triple bond on this side with the nitrogen. Like that. Okay, that's a possibility also. Now, how do we tell which one is best? Let's see. We're going to get to that formal charge. Next slide. Let's see. Did we talk about trying to think of the correct word. Oxidation reduction reactions where electrons are transferred. Have we talked about that yet? Okay. And in order to determine oxidation states, oxidation state is a bookkeeping scheme, right? Where you determine, right, what's the oxidation state here? This would be +1. This would be say, no, that's not a good example. Let's just say oxidation state is one way to track electron movement, but in organic chemistry, it's usually more efficient to go to formal charge instead. It's just another bookkeeping scheme. And it's the difference between the number of valence electrons on the free atom and the number of valence electrons assigned to the atom in the molecule. So in this case, let's see, let's draw them separately so I can work underneath. Draw this one over here. There we go. Okay. So what's the number of valence electrons for each one of these? Well, oxygen has 6, carbon has 4, nitrogen has 5 on the separate atoms, right, from the periodic table. How many are assigned to each one? Well, lone pairs are assigned to the atom they're sitting on. So that means this has 2, 4. Bonds, you only get half of them. So that's 2, 4, 5, 6. Minus 6 equals 0. This is 1, 2, 3, 4. Minus 4 equals 0. This is 2, 4, 5, 6. Minus 6 equals -1. Okay? So we have a 0 for oxygen, a 0 for carbon, -1 for nitrogen. What we're trying to do is minimize the formal charges. So this looks pretty good so far. Let's look at this one. Okay, we still have 6 here, 4, and 5 to begin with. Then we have 2, 4, 6, 7. -7 equals a -1. Then we have 1, 2, 3, 4. -4, still 0. This one we have 1, 2, 3, 4, 5. -5 equals 0. Okay. So we have a similar mix, 0, 0, -1, -1, 0, 0. So how do we break the tie? Which one would be preferred? The preferred one, if you have a negative like this one, the negative should go on the more electronegative atom. So that would be oxygen. Oxygen's more electronegative than nitrogen. So this is probably the preferred structure. We have a similar arrangement, 0, 0, -1, on both of them, but this one puts the negative on the oxygen. And that's the more electronegative. So this is the preferred structure. Okay. And this is just the rules. Right? When you're figuring the formal charge, then you want to start out with what is the free atom, and then you subtract the valence electrons that are assigned to it in the structure. Right? Lone pairs belong to that atom, bonds only half and half. Let's see. Consider this one. Assign the formal charge for each atom in the molecule. All right. Now we're doing on time. 3 o'clock. What do we go to? 350. Yeah, 350. I'm gonna have to pick up the pace. Because we might have to split the review again anyway, and I don't want to have to split the lecture too. Okay, so if we have this molecule where we have phosphorus and 3 chlorines and oxygen. So we have, there's an octet, there's an octet, and these are all octets. Okay. All right, so oxygen starts out at 6, chlorines start out at 7, phosphorus starts out at 5. Okay, so oxygen has been 2, 4, 6, 7. That's -1. 2, 4, 6, 7 for each one of the chlorines. So they're all zeros. Phosphorus starts out at 5, and you have 1, 2, 3, 4. It's a +1, right? So for that structure, phosphorus is +1, oxygen's -1, and all the chlorines are zeros. Now, when we add up the formal charge, we have to equal. Oh, you know what's wrong? Hold on a second. Let's see if I broke the rules earlier. Oh, OCN minus. No, we're good. The total charge on the ion, if there is one, has to equal to the summation of the formal charges. We had a -1 and 0, so it added up to -1. Okay, I'm happy. In this case, it's neutral. So +1, -1, and 0 are 0. Summation of 0. These are known as non-equivalent Lewis structures, and we looked at our example earlier. This is an example using carbon dioxide. And if we find ourselves with non-equivalent Lewis structures that are written validly, then we use formal charge to break the tie. Right? And this particular one gives double bonds to each of the oxygens is the lowest formal charge. Carbon 0, oxygen is 1, 2, 3, 4, 5, 6 is 0. They're all zeros for carbon dioxide. For the other one, there's probably a +1 and a -1. Okay, formal charges are estimates of charge. They're not actually charges. It's a bookkeeping scheme. So when you calculate these values, don't automatically assume that it's a charge. All right, now we're going to get into, now that we know how to draw Lewis structures, we're going to use the Lewis structures to tell us something about geometry. And once we know geometry, then we can say whether the molecule is polar or not. This is the VSEPR model. Valence shell electron pair repulsion. That's a mouthful. All it means is that when you have, I don't know, however many atoms positioned around a central atom, these electrons in their bonds tend to repel one another in such a way as to minimize the repulsive forces. So that means regular structures put them as far away from each other as possible. For carbon dioxide, it's obvious. The best way to do that one is linear, right? Puts these on opposite sides of the atom. That's the most stable arrangement for that molecule. So that's what we mean by valence shell electron pairs repulsion. They're repelling each other. All right. Let's see. They try to maximize distances. And then we have regular geometric shapes that can be assigned to various combinations around a central atom of these. For two, it's always linear. If you have two groups, and we count, if we have a single bond, double bond, triple bond, these are all considered one group each for our purposes. Linear structures are 180-degree bond angle. So the bond angle, use this F is the apex, and the bond angle will be 180 degrees. If we have three like before, say this one, B, H, H, we have three bonds. That would be trigonal planar. It's all in the same plane, but it forms an equilateral triangle. Now, these are not the bonds, they just outline the shape. But the bond angle is here. And the bond angle will be 120 degrees, right? 360 all the way around, right? So if you divide it into three groups, it's 120 degrees each. Tetrahedral, like carbon tetrachloride. That chlorine's in the back. So the base of this tetrahedron is right here, and then we form like that. So the tetrahedron has 4 equal faces. And that's just the outline of the structure. The bonds are still here, right? There, 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 there. And the bond angles here, all of them are 109.5 degrees. At least that's where we start. We'll look at several more later, but that's where we start. Okay, so to apply the VSEPR model, first thing you have to do is draw the Lewis structure for the molecule. Once you have a valid molecule, draw the Lewis structure. count the number of groups around the central atom, and arrange them in a way that minimizes repulsive forces. Now, this also includes lone pairs. All right, so if we had oxygen, right, we had our hydrogens here like that, and like that, like that. So we have 1, 2, 3, 4 groups around there. So 4 groups implies tetrahedron. But we've only got 2 hydrogens. So how do you form a tetrahedron there? Well, you put oxygen in the middle, you have hydrogens here, here, and then you have up here a lone pair, and then over here a lone pair. So those 4 groups around that oxygen lay out a tetrahedral structure. That's called the electronic structure, where you include the lone pairs. Then once you've got the electronic geometry, right, then you just cover up the electrons. Cover up those electrons, and what do you got left? You got a bent molecule. Okay. Now we started off with 109.5 degrees, right, for a tetrahedron. But funny thing about lone pair electrons, if they're not confined in a bond, they tend to go, they balloon, and they put pressure on this bond here. So this bond now is decreased to something like, let me see if I can remember, neighborhood of 105 or 107 degrees. It decreases that angle by this pressure from the outside, from those lone pairs. And that gives you this bent molecule, which is the molecular geometry. We have to do them in that sequence in order to arrive at a valid geometry for the molecule. HCN, right? I think we drew that one earlier. Hydrogen cyanide, right? That's a linear molecule, 180-degree bond angle. pH 3 is trigonal planar. It's trigonal pyramid, excuse me. pH 3 would be like this. If we finish drawing it, we would do, let's see, here, here, here. Let's put the other H back here, H, H, H. So it has this base, and this is your lone pair. So we set it up like this, then we cover that up, and what do you got left? Well, a trigonal base on a pyramid, right? And the bond angle starts out at 109.5, but that pressure decreases it. It's actually 107. And then SF4 is a seesaw. So SF4, let's draw SF4. SF4, let's go the whole route. Sulfur is 6, and then 4 times 7 is 28, so we have 34 electrons. Okay, so we have S, and then we have F's here, 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 and here. So that's 2, 4, 6, 8 is 26 electrons. 2, 4, 6, 6, 2, 6. So 4 times 6 is 24. And we have 2 electrons left over. They go right here. Okay. So how do we do 5? Well, 5, we've gone up to 4. When we have 5 groups, like 1, 2, 3, 4, 5, we have what's called a trigonal bipyramid. And if we draw the, let's do it up here. If we draw the structure, we have this triangle in the middle with sulfur in there. And then we have up here, we have fluorine. Well, with the trigonal bipyramid, fluorine's going to be here and here. And then we're going to have another fluorine here. And let's see, 1, 2, 3, 4, 5. That line goes down to there. We have one here and one here. For a trigonal bipyramid, if you have lone pairs, they go on the triangle. So for the bonds, we get a bond here, get a bond there, and a bond there. Right? And this bond is 180 degrees. And these bonds are right angles. Right? So if we take this one and turn it like that, right, and just ignore these lone pairs, we get a sulfur here. Do I have enough? No, there's 4 fluorines. Hold on a second. 1, 2, 3, 4. There we go. We have one lone pair, sorry. One lone pair. So we get these fluorines here, fluorines here, fluorines here, and fluorines here. The lone pair would have gone up here on the triangle. And that looks like a seesaw. Let's see. Let's do krypton tetrafluoride. This is 8. 4 times 7 is 28. So that's 36 electrons. And we have krypton and 4 fluorines. 2, 4, 6, 8 equals 28 electrons. So 4 times 6 is 24. And that leaves 4 electrons, right? So those 4 have to go here. There, right there. Okay. If we count up the number of groups, 1, 2, 3, 4, 5, 6. 6 groups means octahedron. So I usually draw a kind of a slanted square in the middle. And then a fluorine goes up here. Actually, we have 4 fluorines, right? In the octahedral arrangement, the atoms go on the square, and the lone pairs are at the apex. Right? So an octahedron means 8 surfaces, right? So if we draw down to here, here, and here, here, and then we draw here and here to that other lone pair, and here and here, we get 4 surfaces on top, 4 on the bottom. That's 8 surfaces. That's an octahedron. Now that's the electronic structure. What would be the molecular structure? We'll just cover these up. What do you got? You got square planar. So the electronic structure is octahedral. But the molecular structure is square planar. Right, with 90-degree. If we go from here to here, that's 180 degrees. If we go from here to here, that's 90 degrees. Okay. Molecule that has polar bonds will always be polar. Nope. Depends on the geometry. Lewis structure for CO2, we've done that before. Does it contain polar bonds? Yeah. But it's nonpolar because they cancel out. Lone pairs make a molecule polar. Is that true or false? Lone pairs make a molecule polar. Not necessarily. Like for this one, you got a lone pair on this side and a lone pair on that side, they cancel out. These guys are equally spaced around the krypton, they cancel each other out. So that molecule, even though it has lone pairs, is nonpolar. Come on. Here we go. Xenon tetrafluoride would be similar to this one. Okay, so here's a. Does this come out of your? Yeah, I think this came out of your textbook. What I usually do when I have time is draw. Let me check. How many more slides did I have? Yeah, just a few. What I usually do is set up a table and say, if you have the number of groups, that includes bonds and lone pairs. And then you say electronic structure, right? And then you say lone pairs, number of lone pairs. And then you say molecular structure. Okay. So we're not even going to say one. If you have two, of course, it's obviously linear. So let's go to three. If you have three groups, then the electronic structure is going to be linear. Right? If you have a lone pair, if you have no lone pairs, it's still going to be linear. If you have one lone pair, it's still going to be linear. That's an easy one. If you have four groups, oh, excuse me, that's not right. That's two groups. Sorry, two groups. Three groups are trigonal planar, right? And obviously, if you have no lone pairs, you're going to have trigonal planar over here. So I'm not going to do that one. If you have one lone pair, then you have a bent molecule. If you have two lone pairs, then you're linear. So that just takes up space. Four is tetrahedron. Okay. Now, if you have, of course, if you have no lone pairs, it's tetrahedron again. If you have one lone pair in a tetrahedron, now you have a trigonal pyramid. Let's see. Let's examples. Carbon dioxide. That's a good one. Trigonal planar, say boron trifluoride. Oh, we need one with one lone pair. One lone pair, that would be no lone pairs. One lone pair would be, I can't even think of one. They give us an example. No. Okay. I have to think of one. Let's see. Well, if you have two lone pairs here, you're going to have a linear molecule. Tetrahedron trigonal pyramid. Oh, a good one for that one is ammonia. Yeah, that's got one lone pair. If you have two lone pairs, Then you have linear. I don't have an example for that one. If you have 5 groups, then the electronic structure is going to be a trigonal bipyramid. Okay. If you have 1 lone pair, then you're going to have a square. No. If you have 1 lone pair, let's back up, trigonal pyramid. 1 lone pair is going to be, 1 lone pair is going to be on the triangle. So that's a seesaw. If you have 2 lone pairs, then you're going to have T-shape. Okay. And 3 lone pairs is linear. And then the last one is 6 is octahedral. Octahedral. So if you have 1 lone pair, it's going to be on one of the apexes, which means a square pyramid. If you have 2 lone pairs, you're going to have a square planar. Let's see, if you have 3, then one of them is going to be taken off of the, if you have 3, then you're going to have T-shape again. Maybe your textbook will give you some examples, if I don't have any in here. Okay, is this our last one? I think so. Yeah, this is well, it's next to our last one. Okay, you got all that down? Yes. Okay. Hopefully this kind of organizes things so you always have to start with the electronic structure and put your lone pairs in, and then you cover up the lone pairs and see what's left. All right. When phosphorus reacts with excess chlorine gas, the compound phosphorus pentachloride is formed. In the gaseous and liquid states, this substance consists of PCl5 molecules. But in the solid state, it has a 1-to-1 mixture of PCl4 plus and PCl6 minus. PCl4 plus and PCl6 minus. So you have 1-to-1 ratio of these two in the solid. What's the geometry of each one of these? Oh, here's PCl5. PCl5. Okay. So phosphorus is 5 valence electrons. 4 times 7 is 28 minus 1, right? Because that's positive. And this is 5 times 7 is 35, right? And this is 6. Is that right? Yep. This is 6 times 7 is 42 plus 1 for that minus. Okay, so we have 33, 32, right? 32 electrons. Yep. And this one is 40 electrons. And this one is 48 electrons. Okay. So we start off with phosphorus in the middle, 4 chlorines, right? 2, 4, 6, 8 minus 8 equals 24 electrons. So 6 times 4 is 24. Okay, so this one's going to be tetrahedral, right? 4 groups around the central atom. Let's see, this one is neutral, and we got 5. So phosphorus in the middle, and we've got 1, 2, 3, 4, 5 fluorines. Two, 4, 6, 8, 10. Use 30. So if we do 6 times 5, that's 30. That covers all the electrons. Okay. This is actually, that's correct. This one is neutral, so I don't have to put a bracket around this one. This one is trigonal by pyramid. Okay. And this one is P 1, 2, 3, 4, 5, 6. Chlorine, 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 chlorine. 2, 4, 6, 8, 10, 12 equals 36 electrons. 2, 4, 6. 6 times 6 is 36. Use up all the electrons. Don't have any lone pairs. There we go. This is octahedral. Okay. Oh, make it official. There we go. So this one's trigonal by pyramid, PCl5. This one, the plus, the cation is tetrahedral. And the last one should be octahedral. There we go. Noble gases are not expected to be, since all their valence orbitals are filled, they're not expected to be chemical reactive. For many years, we thought that. But in the 60s, compounds were formed with krypton, xenon, and radon. So they went down to here and formed compounds with them. Because the electrons, the valence electrons in these are way, way out there. They're not as tightly held as these guys. You're not going to get a compound with that one, that one. I may have seen an argon compound, but they're not, they're pretty rare. And they may be short-lived. All right. Okay, here's the last one. Oh, good. We got time. So, xenon tetrafluoride. Does it have a dipole or not? Right. That's 8, and 4 times 7 is 28. So that's 36 electrons. Fluorine, 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 fluorine. 2, 4, 6, 8. 28. So that's 4 times 6 is 24. And that leaves us 4 electrons. So we have a lone pair there, lone pair there. So we have groups, we have 6 groups around that, which is octahedral electronic. But we have some lone pairs. So we got to put the lone pairs where they belong. We had the xenon, not the X. Thinking like Elon Musk. Xenon in the middle. Now with lone pairs in an octahedral arrangement, they go in on the apexes. So they'll be up here and down here. And the fluorines go on the square. Right there, there, there. All right, so I predict that this would be a nonpolar molecule. No dipole moment. The other possibility is if we put the two pairs, lone pairs, on the square, like we did with the trigonal bipyramid, right? In which case we would get a seesaw. But if we got a seesaw, then the molecule would be polar, right? It'd be unbalanced. Predicting nonpolarity agrees with the data. Square planar molecule structure agrees with the data because we try to measure the polarity of the molecule and get nothing. It's nonpolar. No dipole moment, which means this is the preferred structure. Okay.